So in this tutorial, I'm going to show you how to calculate the gradient of a scalar field using ComFiT. And to begin, I have already installed ComFiT, and here I'm importing the necessary packages, ComFiT, NumPy, and SciPy for Fourier transformation. Now the function that we're going to be calculating the gradient of is the scalar field, which is a function of x and y. It's a cosine and a sine consistent with the periodic boundary conditions, and if I create a system with dimension 2, and then I calculate the function g with the cosine and the sine, and then I plot the field, and you can see how the function looks. It has these peaks and these troughs, and we're going to calculate the gradient of this function. So to begin, we need to calculate the derivative in the x and y direction, because that's what the gradient is. So remember, the gradient of a real field, so nabla g, is equal to, it has two components. It's the derivative with respect to x of g, and then the derivative with respect to y of g. And so that's what we need to calculate. So first of all, we need the Fourier transform of the g function, SciPy fft.fftn g. And then we're going to calculate the derivative of the g function in Fourier space, which is the unitary vector multiplied by sys.k of 0 times gf, and then the derivative with respect to x then becomes the inverse transform of that, dxg f. And as I said previously, whenever we're taking these Fourier transforms back and forth, sometimes you might be left with some redundant imaginary terms. So I'm just going to take the real part of that just to make sure that it's real. Now do the same thing for the y. So we need dyg in Fourier space. Now this combination here of 1j times sys.k of 0 or k of 1, it's so often used in the ComFiT library that it's also saved in this variable here. So df of 0, di, this I component, and it's the y component I need. So times gf, and then I need to return to real space. So fft.iftn dyg in Fourier space. So that should be that, and then I just need to calculate the gradient, which is the which has two components, the dxg and dyg. So I get dxg dyg gradient. And if I want to plot this, I need to plot it as a vector field. So I do sys.plot vector field of gradient, and you can see that we get this figure here, which has that the arrows shows that the gradient is pointing away from the troughs and pointing towards the peaks, as a derivative would do. Of course, we can also calculate this doesn't tell us anything about the magnitude of the gradient field. So to get that, we need to calculate the magnitude, which is the gradient, which is the square root of the squares of the components plus gradient of the y component, and then the square root of all of that, which we then can plot. Now this is a scalar field, so we need to plot it as such. So sys.plot field mag, and we get this, which shows us the magnitude of the vector field that we plotted here. So it's large here, 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 here. You can see it's kind of big here, 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 and here, and then it's 0 there, 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 and there, which is what you're seeing here with these zeros of this field here. So that is how you calculate the gradient of a scalar field using ComFiT.